right now, you are probably micromanaging an AI.
Oh, almost certainly.
Right. Like you sit down, you have this task in mind, and you just start typing a prompt. You tell the model what to do.
And it spits out a response.
Exactly, but it's not quite right. So, you tweak the prompt, you say, no, make it more concise.
And it replies.
Yeah, and then you say, wait, don't use that specific library, use this other one.
Right, and in the process of doing that, it completely breaks the syntax of the first paragraph.
Yes. Suddenly you realize you've spent like the last 2 hours babysitting a language model.
Yeah.
Word by agonizing word.
Yeah.
Just trying to drag it across the finish line.
It is exhausting. I mean, we have all been there. You end up feeling less like a software engineer or a creative and more like a really frustrated translator.
Just constantly repeating yourself to someone who isn't getting it.
Exactly. The cognitive load of prompt engineering is actually incredibly high.
And that frustration, that exact feeling is what we are tackling in today's deep dive. Because what if I told you the era of the perfect prompt is essentially dead?
It really is.
We are looking at this massive fundamental shift happening right now in software development. We're unpacking a concept called loop engineering.
Yeah, and if you follow what top engineers are doing right now, this has rapidly evolved way past prompt engineering.
Past context engineering, past harness engineering, all of it.
The whole paradigm has just completely shifted. We're moving from a world where humans push buttons to make the machine think,
Right.
to a world where the machine thinks in a continuous loop and humans just, set the boundaries.
So our mission for you today is to demystify exactly what loop engineering is. We're going to break down its core components, the actual mechanics under the hood, and show you why designing autonomous systems is basically the absolute most critical new skill for you to learn.
We have to, because otherwise you're going to get left behind.
Right. And to do this, we've synthesized a mountain of current information. We've got Adi Osmani's latest architectural breakdowns.
Some really deep academic research on self-adaptive systems, too.
Yeah, plus the current thinking from the teams at Anthropic and OpenAI.
Because if you don't grasp the mechanics of this shift, like you said, you're going to be stuck doing manual labor in an automated world. The interaction with AI has fundamentally broken out of the chat box.
Let's frame this up right out of the gate with an analogy. If prompt engineering was like micromanaging an intern, giving them step-by-step instructions, checking every typo, literally standing over their shoulder.
A nightmare for everyone involved.
Exactly. Well, loop engineering is like hiring a highly competent, self-directed manager.
Oh, that's a good way to put it.
You give this manager a goal, and they check their own work. They course correct automatically when they hit a wall. And they only come back to you when the job is completely done and verified.
That hits the nail on the head. But to really understand how to build these self-directed systems, we first need to look at why the industry is abandoning manual prompting entirely.
Okay, so what's the core definition here?
Loop engineering, at its core, is the design of iterative systems. It's where AI agents take an action, observe the results of that action, verify their own work, and then adjust automatically until a goal is met.
Without needing a human to sit there and type, try again every 5 minutes.
Exactly. There's a quote from Peter Steinberger recently that perfectly illustrates this.
Oh, I saw this one.
Yeah, he basically said, I no longer prompt Claude. I design loops that do it for me. My job now is to write loops.
It's the finality of that statement that really grabs you. My job now is to write loops.
Right. And he is far from alone. Boris Cherny, he leads the Claude Code project over at Anthropic. He's been pioneering this exact shift.
Because they're realizing they don't just need to build smarter models.
Exactly. They need to build the infrastructure for these models to run autonomously. A smart model sitting idle, waiting for a human prompt, is just wasted compute.
But I want to make sure people know this isn't just some trendy new framework invented on a tech blog yesterday.
Oh, not at all.
This whole concept of automated feedback loops is deeply grounded in computer science theory. It's based on decades of research into self-adaptive systems.
Yeah, if we look at the broader academic literature, it points us directly to the MAPK model.
Okay, MAPEK. Break that down for us.
It stands for Monitor, Analyze, Plan, Execute, and Knowledge.
Got it.
This has been the theoretical blueprint for how a complex system adapts to changes without a human pulling the levers way before large language models even existed.
Okay, so MAPK sounds a bit abstract. How does that actual cycle function when we're talking about, say, an AI writing code?
Think of it as a continuous control loop. First, the system monitors its environment.
So it's plugged into your code base, watching for errors.
Exactly. When it spots a bug, it moves to the analyze phase. It parses the error logs, figures out why the crash happened. Then, it creates a plan to fix it.
And then execute.
Right, where it actually writes and deploys the new code. And finally, the K stands for knowledge.
Okay, so it learns from it.
Yes, it updates its own internal state with the context of what just happened. That way, it doesn't make the exact same mistake in the next loop.
That actually reminds me of a discussion from the sources where someone compared manual prompts to manually piloting a drone with a joystick.
Oh, yeah, that's a great comparison.
Right, if you're flying manually, you have to constantly adjust for every single gust of wind yourself. But loop engineering is like programming an autonomous flight path.
You just set the GPS waypoints.
Exactly. And the drone figures out the altitude, the wind resistance, the rotor speed, all entirely on its own to hit those targets.
Precisely. You are managing the trajectory, not the raw mechanics of the flight.
But wait, let me push back here.
Okay, go for it.
If we just hand the AI the keys to the codebase, set a destination, and walk away, how does it actually know what good looks like?
That is the million-dollar core.
Because if I tell an autonomous agent, fix this memory leak, what's to stop it from just running in circles, deleting half the application, and then proudly declaring the leak is gone because the app won't even launch anymore?
Which you would totally do. You cannot just unleash a raw language model and hope for the best.
Right.
To keep the AI from driving off a cliff, developers are relying on a highly structured architecture. You have to build a rigorous track for it to run on, with guardrails.
And that brings us to the actual mechanics. How are teams building these tracks? Because Adi Osmani and Cobus Grayling have both been mapping this out.
Yes, they outline what they call the 5+1 fundamental blocks of a loop.
The anatomy of the new software development lifecycle, basically.
Let's unpack it. The very first piece of the puzzle is automations, or scheduling.
A heartbeat.
Exactly. An autonomous system has to know when to wake up. It isn't sitting there waiting for you to type a prompt into a text box.
So these are scheduled tasks that actively discover work, like tying the loop directly to your continuous integration pipeline.
Yep. The second a build fails on GitHub, the loop is triggered.
The AI wakes up, sees the failure, and gets to work before you even get the Slack notification that the build broke.
Exactly.
But wait, how does it handle that without getting overwhelmed? Because a failed CI log can be like tens of thousands of lines long. Doesn't that just burn through the model's context window instantly?
Well, that's where the engineering part of loop engineering comes in. You don't just dump the raw log into the LLM.
Okay.
The automation block includes filtering mechanisms. It extracts the stack trace, identifies the specific failing test, and only feeds the relevant slice of context to the model.
So it's highly curated telemetry.
Exactly.
Okay, so the AI is awake, it has the curated error log, it has a task. But if it just starts rewriting your main Python file directly in your live repository, that sounds like a recipe for total disaster.
Total disaster. Which is why the next crucial block is work trees.
Like Git work tree.
Yes, this is all about isolating the state. If you have multiple autonomous loops running, say, one is fixing a bug, while another is trying to optimize a database query.
You can't have them stepping on each other's toes.
Right, they can't be overwriting the same files.
So a work tree basically provides an isolated sandbox. The AI can experiment, break things, compile, fail repeatedly, all without corrupting the main project.
It checks out a hidden parallel version of the codebase. It does its messy work in the shadows, but this introduces a new problem.
Oh, I know this one. Because if it spins up a completely fresh, isolated sandbox every time it wakes up, doesn't it lose all the context of the project?
It does.
It's like having a brilliant engineer who suffers from total amnesia every time they sit down at their desk.
They wouldn't know your coding standards.
Right, or your architectural patterns, or why certain legacy decisions were made.
And that amnesia is exactly what the third block solves. Skills.
Okay, so how do we give it skills?
To prevent the AI from reinventing the wheel on every single task, developers are injecting persistent knowledge files directly into the repository.
Like actual files in the code base.
Yeah, you'll see files named skill.md or claude.md sitting right next to the source code.
So it's the K in the MPEK model coming to life, the knowledge base.
Yes. When the loop spins up its work tree, the very first thing it does is read that skills file.
And what's in it?
It contains the hard rules, like we use functional programming paradigms here, or never use this deprecated library.
Or always format database queries this specific way.
Exactly. It gives the loop a persistent memory of the project's DNA.
Okay, so now our AI is awake, it's in a safe sandbox, it remembers the rules of the house. but it's still trapped inside a text editor.
Right.
If I tell it to fix a bug, it might need to go read the original user report in a Jira ticket or check a production metric in AWS. How does it reach outside the code base?
That is the fourth block, plugins and connectors. Specifically, the industry is standardizing around things like MCP, the Model Context Protocol.
Because an AI in a vacuum isn't very useful.
It needs hands and eyes in the real world.
I want to dig into MCP for a second because it sounds like magic. How does it actually work? Does the LLM just inherently know how to navigate Jira's API?
Not at all. And that's the brilliance of MCP. In the past, you had to write custom, brittle code to teach the AI how to authenticate and parse every single external tool.
Which was a nightmare to maintain.
Exactly. MCP changes that.
Yeah.
X is a standardized client-server protocol. The LLM is the client. Your local machine runs MCP servers that securely expose specific tools.
Like your local file system or your Slack workspace or GitHub issues.
Yes, the LLM just says, I need the context of issue number 42. And MCP translates that request, fetches the data, and hands it back to the model at clean, formatted text.
So it abstracts away the whole integration nightmare.
Entirely.
So the agent can seamlessly pull a Jira ticket, write the code, and then post a summary of its work in a Slack channel, all through standardized pathways.
Exactly. Which brings us to the fifth block. And this is arguably the most critical for keeping this entire system from collapsing.
Okay, what is it?
Subagents, specifically the maker-checker dynamic.
This is fascinating to me. So instead of just having one AI doing the work and declaring it finished, you actually deploy two separate agents.
Yes. You have one AI acting as the builder, writing the code, and a completely separate AI agent acting as the checker.
Whose only job is to verify the maker's work.
It introduces a built-in system of checks and balances. The maker writes the function, and the checker tries to break it.
But hold on, let me stop you there. If the maker agent is powered by, say, Claude 3.5 Sonnet, and the checker agent is using that exact same foundational model, aren't they going to share the same blind spot?
That is a very valid concern.
Right. Won't the checker just look at the maker's hallucinated logic and say, yep, looks like perfect logic to me? Because they literally share a brain.
That is a phenomenal point, and it's a trap a lot of early loop designs fell into.
Oh, really?
Yeah. If the checker is just eyeballing the code using its LLM intuition, it will absolutely rubber stamp hallucinations.
So how do you fix that?
The secret to a robust maker-checker dynamic is that the checker doesn't just read the code, it executes tests.
Ah. So the ground truth isn't the LLM's opinion. The ground truth is the compiler.
Exactly. The loop is often driven by test-driven development.
So the maker writes the code.
And the checker writes a rigorous unit test for that code and then actually runs it in the work tree.
And if the test fails?
The checker doesn't just say, bad code. It takes the execution error log, hands it back to the maker, and says, your code failed on line 42 with a type mismatch. Fix it.
The compiler acts as the objective referee between the two agents.
Yep.
It's guaranteed AI workplace drama. I just picture these sub-agents arguing like a human dev team in a Slack channel.
They kind of do.
The maker proudly declares, I implemented the new feature flawlessly. And the checker instantly replies, rejected. It failed 3 unit tests, and your syntax violates the rules in skill.md.
It is a dramatic dance, but it's highly effective.
It actually reminds me of a great analogy from the reading about a robot chef.
Oh, the recipe one.
Yeah. The old way prompt engineering is handing a robot chef a recipe. It just follows it blindly from top to bottom. If you accidentally typed 1 cup of salt instead of 1 teaspoon of
That's what the robot will dump in a cup of salt.
and serve you an inedible meal because it did exactly what it was prompted to do.
Right, because it has no feedback mechanism.
But the maker-checker loop is like a robot chef that actually tastes the dish as it cooks.
Yes.
It adds a little salt, tastes it, realizes it needs more acid, adjusts the spices, tests it again, and only decides it's ready to serve when the flavor profile perfectly matches the target.
And the best part is, you aren't even in the kitchen.
Exactly.
That tasting mechanism is exactly what the checker agent does. But to manage all this back and forth, we have to talk about the final piece of the architecture. The +1 in the 5+1 model.
Which is...
Memory or state.
Because if the maker and checker are arguing for 4 hours, tweaking code and running tests, an LLM is eventually going to hit its context limit, right?
Right.
It's going to forget what it tried 3 hours ago.
Precisely. Language models are fundamentally stateless. If a complex task takes 50 iterations, the context window gets bloated, and the model starts hallucinating or just repeating failed attempts.
So how are developers solving that?
They're implementing persistent state trackers,
Okay.
essentially digital markdown whiteboards.
Okay.
Before the agent takes its next action, it writes down what it is currently doing, a summary of what it has already tried that failed, and what its next logical step is.
So it's leaving breadcrumbs for itself.
Exactly.
Yeah.
Tools like Claude Code are already implementing these exact primitives so the loop can maintain long-term coherence without human intervention.
Okay, so let's recap. We have automations to wake it up, work trees to keep it safe,
Skills to give it memory,
plugins to give it reach, the maker-checker dynamic for quality control.
and state to keep it focused.
When you put all of that together, what does this actually mean for the people doing the work? Because this completely changes the economics of software development, doesn't it?
It fundamentally alters the equation. On the benefits side, the acceleration is just staggering.
I can imagine.
When you have agents iterating, failing, running tests, and course-correcting at machine speed, you are talking about completing development cycles in minutes that used to take human engineers hours or even days of tedious debugging.
And we are seeing hard data to back this up in the source.
We are.
If you look at improvements in complex benchmarks like Terminal Bench, the jump in autonomous problem solving is massive. It aligns perfectly with established principles of control engineering.
Which is?
When you automate the verification step, you naturally raise the baseline quality of the output. Plus, it allows a single human developer to scale infinitely. You can have 10 loops handling 10 different GitHub issues all in parallel.
But we have to look at the dark side of this equation.
Yeah, let's unpack the risks.
Because the mechanics of loop engineering bring some very significant perils along with that payoff.
What happens when the loop goes off the rails?
Well, the most immediate risk is financial. Token costs can absolutely skyrocket.
Because you are paying for the compute based on the amount of text processed.
Exactly. Let's say the maker writes bad code. The checker fails the test and feeds the error back. But the maker misunderstands the error and writes the exact same bad code again.
And the checker fails it again.
If this maker-checker dynamic gets stuck in an unresolved argument and there's no human supervising it, it will just loop indefinitely.
A literal infinite loop of expensive AI compute.
Yep.
And because it's passing the history of the conversation back and forth, the context window is growing exponentially with every single iteration.
Which means the cost per token is going up every time.
That is terrifying for any engineering manager's budget. A runaway loop over the weekend could cost thousands of dollars.
Oh, easily. You are paying for every single token of that automated argument. But the risks go beyond just the compute budget.
Right, there are security issues.
Massive ones. Having unattended agents dynamically modifying code bases, installing libraries, and interacting with live systems introduces huge vulnerabilities.
Because if a loop is compromised, or even just if it hallucinates a solution that involves pulling in some unverified third-party package.
It can introduce malicious code into your environment without a single human ever reviewing it. In ML systems, positive loops can actually amplify biases and errors.
That leads directly into a concept from the deep dive that really chilled me.
What's that?
It's the idea that in this new paradigm, done is a claim.
Yes, done is a claim.
Meaning, when the AI loop finally stops, pings you on Slack and says, the memory leak is fixed, I'm done. That is merely a claim. How do you actually trust it?
This is the absolute crux of the issue. You can't blindly trust it, but at the same time, verifying it becomes incredibly difficult.
It creates what's being called comprehension debt, or cognitive surrender.
Cognitive surrender, it's a heavy term.
And this is where it feels really visceral for me. Because when you write code yourself, you build a mental model of the system in your head.
Right, you know how the pieces fit together.
Exactly. But if an autonomous loop writes 10,000 lines of complex back-end architecture while you sleep, your mental model is totally obsolete.
You've surrendered your cognitive understanding of your own product.
It's exactly like being in a self-driving car.
Oh, that's a perfect analogy.
It is a miraculous invention right up until the exact millisecond the sensor fails and it doesn't see a barrier. You still have to keep your hands near the steering wheel.
Always.
If you completely surrendered your understanding to the AI loop, when a critical production bug eventually hits at 3 a.m., you won't even know how to begin fixing it because you didn't write the code.
You didn't even manage the writing of it.
You just watched it happen. The debt comes due all at once.
And this raises an incredibly important question for you, the listener. If you are no longer typing the code, and you are no longer even typing the prompts to generate the code, what exactly is your job now?
And that transition is exactly where we need to land today. Keeping our hands on the wheel means the human role isn't disappearing, but it is fundamentally evolving.
We are shifting from being reactive tool users to being the architects of autonomous partners.
We are moving one step further up the abstraction layer.
Exactly. You are no longer the painter applying the brushstrokes. You are the architect designing the building.
Your job is to design the system, define the rigid constraints in that skills file, build the safety rails, and carefully monitor the telemetry of the loops.
We want to give you some actionable takeaways to end on, because listening to this theory is one thing, but experiencing the shift firsthand is another.
We challenge you to try implementing a very basic loop today.
And the easiest way to start is with that third architectural block we discussed, skills.
Yes, take a small step. Create a simple skill.md file in the root directory of whatever project you're working on right now.
Just write down the core rules of the project.
The tone, the specific libraries to use, and the architectural patterns to avoid. Then, try using a /goal command in an environment like Claude or Grok and just point it at that file.
Stop giving it step-by-step prompts.
Yeah, and just see how it behaves differently when it has persistent state and boundaries.
And for the more advanced listeners out there, try designing a basic triage loop.
Ooh, how would they do that?
Set up an automation that triggers whenever a new issue is submitted to your repository. Have a simple agent read the issue, categorize it, and attempt a first-pass fix in an isolated Git worktree.
You don't have to merge it, just see if it can successfully navigate the loop.
Exactly. Just remember the golden rule of this new era: trust, but verify.
Yes. Let the maker and the checker do their dramatic dance in the sandbox, but you are still the one who signs off on the final deployment. Don't let your comprehension debt bankrupt you.
You know, there's one final thing to chew on here. Building on that idea of the maker-checker dynamic.
What's that?
We talked about how loop engineering means we are now essentially creating and managing these teams of AI sub-agents to do the heavy lifting for us.
Right, managing the autonomous AI workforce.
But if we extrapolate this trend just a little bit further into the future, how long until we just ask an AI to design the optimal loop for us?
Oh, wow.
Will the next phase of software development just be humans managing an AI whose only job is to design custom loops to manage other AIs?
Are we about to be engineered right out of the loop entirely?
It's a real possibility.
We go from micromanaging the intern to realizing the intern just built a fully automated factory that doesn't need a manager at all.
Pretty wild to think about.
That is definitely something to think about the next time you catch yourself tweaking a prompt for the 5th time. Thanks for taking this deep dive with us.